Hello everyone, this is Bsc second year real analysis first class. So we have started the new concept, that is the real sequences. So what is meant by sequence? It is a function f from a set of natural numbers to real number. Special function from a set of natural numbers to set of real numbers is called a sequence. So we have discussed what is meant by bounds of a sequence. When does call the sequence is bounded above, when does call the sequence is bounded below, and when does call the sequence is bounded. So today I am going to discuss convergence of a sequence. Convergence of a sequence. Convergence of a sequence. It is a very important part of this chapter, that is sequence of the real numbers. Now write down the definition of convergence of a sequence. A sequence Sn is said to be convergence to a real number L is said to be convergent to a real number L or to have a limit L. A sequence Sn is said to be convergent to a real number L or to have a limit L if for given epsilon greater than 0 if for given any epsilon positive there exists M belongs to capital N, M belongs to natural numbers such that mod of Sn minus L is less than epsilon for all n is greater than or equal to n. Now understand what is meant by convergence of a sequence. A sequence Sn is said to be convergent to a real number L or to have a limit L as n tending to infinity if for a given epsilon positive, epsilon is any small positive number that we have given. Then there exists M belongs to capital N. Then there exists capital M which may be very large, such that Sn minus mod of Sn minus L is less than epsilon for all n greater than or equal to M. Now understand what does the definition is actually says. So Sn minus L, the difference between the elements of the sequence and L is become small and small as we go n which is greater than m, where m is a very large, maybe large. That is, the difference between the L and elements of the sequence is goes smaller and smaller, and at one stage the difference between the elements of the sequence and L goes to 0, tending to 0, which is very small. So understand the definition of the convergence of the sequence. Now note one. Now if Sn is convergent, if the sequence Sn is convergent, then according to the definition of convergence is less than epsilon for all n greater than or equal to m. Now from this identity we can write L minus epsilon is less than Sn is less than L plus epsilon. So from this we can directly say that every convergent sequence is bounded because every element of Sn is greater than or equal to N minus epsilon and every element of Sn is less than or equal to N plus epsilon. Also from this we can write L is a limit point of this sequence. Then L, which is any real number, is limit point of the sequence. Limit point of the sequence. And so, from this, we can say that every neighborhood of L contains every neighborhood of L contains infinitely many points of Sn. Contains infinitely many points of the sequence Sn. Now note number 3. Only finitely many points of the sequence can lie outside in any neighborhood of L. Which says that only finitely many elements of the sequence can lie outside any neighborhood of L. So this is note number 3. Now, Theorem 1. Every convergent sequence is bounded. Theorem. Every convergent sequence is bounded. Theorem 1. Very important theorem. Every convergent sequence is bounded. Every convergent sequence is bounded. Proof. Let the sequence Sn is converges to L. Now let the sequence Sn which converges to a real number L. So from this we can write Sn minus L is less than epsilon for all n greater than or equal to L according to the definition of convergence. Now from this we can write L minus epsilon is less than Sn is less than L plus epsilon, where epsilon positive. Now consider two sets. And so let G is equal to minimum of L minus epsilon S1 S2 dot 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 Sm, and capital G is equal to maximum of L plus epsilon S1 S2 Sm. So observe these two sets. G is the minimum of elements in between these two, and capital G is the maximum of elements in this two. Also, I note that every element of a cell lie inside these two numbers. Every element of inside these two numbers. So we can directly say that small g is a lower bound of the sequence, and capital G is the upper bound of the sequence. Which implies that small g is lower bound of the sequence Sn, and capital G is upper bound of the sequence Sn. So from this we can write small g is less than or equal to Sn is less than or equal to capital for all n belongs to the set of natural numbers, because in sequence domain is always set of natural numbers. This implies that the sequence Sn is bounded. This theorem says that a sequence is convergent, then it is bounded. That is, every convergent sequence is bounded. Now, I am going to discuss about the converse of this theorem. Converse of this statement is, if the sequence is bounded, then it is convergent, which is false. No. The converse of this theorem, the converse of the theorem may not be true. The statement of the converse is, if the sequence is bounded, then it is convergent, which is false. Example: Sn sequence minus 1 to n, this is nothing but minus 1, 1, minus 1, 1, and so on. Now this sequence is bounded. This sequence is bounded because minus 1 is less than or equal to Sn is less than or equal to n for all n belongs to set of natural numbers. This sequence is bounded. So sequence Sn is bounded, but not bounded. Now, Theorem 2. A sequence cannot converge to more than one limit. Theorem 2. A sequence cannot converge to more than you can write this statement in another form. If a sequence is convergent, then it has unique limit point. So understand the statement first of the Theorem 2. A sequence cannot converge to more than one limit. So if the sequence is convergent, then the limit of convergence is 1. Limit of convergence means the sequence, the real number L such that the mod of Sn minus L is less than epsilon for all n greater than or equal to m. If the sequence is convergent, then it has a unique limit point. Now proof. Proof. Let the sequence Sn converges to L and L dash, which is L is not equal to L dash. So I am going to prove this theorem by method of contradiction. So assume that the sequence Sn converges to two limits, L and L dash. So after I am solving this, then we got some contradiction, and there our supposition is wrong. Therefore, the sequence has a unique limit. Now, if L and L dash are the two limits of the sequence, there exists m1, m2 belongs to set of natural numbers such that Sn minus L1 is less than epsilon for all in L is greater than or equal to mn, and Sn minus L is less than epsilon for all n greater than or equal to m. According to the definition, we can write like this. Now let epsilon be 1 by 3 L minus L dash, which is positive. We choose epsilon 1 by 3 difference between L minus L dash. Now consider L minus L dash. We can write it L minus Sn plus Sn. We add and subtract Sn from this identity minus L dash. So we can write it as is less than or equal to L minus Sn is what? L minus Sn is this epsilon. L minus Sn plus Sn minus L. So this is what epsilon. This is what epsilon. So which is less than 2 epsilon. Which is less than 2 epsilon. So L minus L dash, which is less than 2 epsilon. But epsilon is what? 1 by 3 mod of L minus L dash, which is equal to 2 by 3 mod L minus L dash. So you can observe that L minus L dash is less than 2 by 3 L minus L dash. So these two are the same numbers, and one which is less than 2 by 3 times second. So which is false? False. Hence our assumption is wrong. Hence assumption is wrong. Hence we can write directly that L is equal to L dash. So this happens only when L is equal to L dash. Hence the proof. Now, combining these two theorems, theorem first and theorem second, we can write theorem 3 Theorem first says that every convergent sequence is bounded. Theorem second says that if it is convergent, then it has a unique limit. So we can combine these two theorems to write the theorem 3. Every convergent sequence is bounded and has a unique limit. Every convergent sequence is bounded and has a unique limit. So by combining these two theorems, we can write theorem 3. If the sequence is convergent, then it is bounded and has a unique limit. So we can discuss some example. Sn is equal to 1 by n. N belongs to set of natural numbers. So this sequence is 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by n, and so on. The limit of the sequence is 0, and this sequence is converges to 0. Hence, it is bounded because 0 is less than or equal to Sn is less than or equal to 1, and it is converges to 0. Now, if the sequence Sn notation, if the sequence is converges to L, then we write limit n tending to infinity Sn equal to L, or Sn tending to L